Hello everyone. My name is Gwangwook Park from Chungnam National University. Today, I will present our work, EG-3DVG, Expression and Geometry Aware Grounding Decoder, for 3D visual grounding. The 3D visual grounding is to localize a target object within a 3D scene, based on a text description. For example, input text query like the white desk. This is under the pictures. The model processes the complex 3D scene and text to output the exact target object's bounding box and semantic mask. Despite recent advance, existing methods face three limitations. The first is intra-category confusion, where models fail to distinguish between multiple objects of the same category, like chairs or tables. This is because current frameworks struggle to capture fine-grained expression cues in the text description. The second is cross-modal misalignment. Conventional cross-attention fails to reliably align the two modalities because visual tokens encode explicit 3D positional data, whereas text tokens completely lack spatial context. This imbalance leads to incomplete text-vision alignment. The third is geometric reasoning errors. Existing models often misinterpret the 3D spatial configurations of surrounding points and background regions. Without a mechanism for selective feature aggregation, this leads to inaccurate localization and poor mask predictions. To explicitly address these challenges, we propose a unified framework called EG-3DVG. It consists of three core components. First, ECL for enhanced discriminative power. Second, PECA for reliable cross-modal alignment. And third, GMA for robust spatial context reasoning. Now, let's look at the overview of our proposed framework. First, we use Roberta and PointNet as our backbones to generate text and visual tokens from the input text and 3D point cloud. These tokens are then fused via a cross-modal encoder. From the encoder's visual tokens, we derive two representations to feed into the decoder: candidate tokens and superpoint tokens. These candidate and superpoint tokens, along with the text and visual tokens, are then fed into our expression and geometry-aware grounding decoder for joint refinement. To resolve intra-category confusion within this process, we introduce expression-aware contrastive learning. Specifically, we take the refined candidate token from the decoder that corresponds to the ground truth target object. We then contrast this single target token against both positive text features and sampled negative text features from same category distractors. As illustrated in the diagram, expression and geometry-aware grounding decoder processes information through two branches, the superpoint token branch and the candidate token branch. The superpoint branch takes superpoint features and enriches them by integrating contextual semantics from text tokens and object-aware cues from candidate tokens. In parallel, the candidate branch refines the candidate tokens by incorporating cues from text, visual, and refined superpoint tokens. Within this decoder architecture, we introduce two complementary attention modules to overcome previous approaches. First, the position-guided expression cross-attention module bridges the spatial gap between modalities. Since text tokens inherently lack explicit spatial context compared to 3D visual features, PECA projects 3D positional embeddings from point coordinates and injects them directly into the text tokens before cross-attention computation. Second, to address the incomplete spatial coverage of candidate tokens, our geometry-aware masked attention module enriches candidate features by exploiting the full set of visual tokens. To suppress interference from irrelevant objects or background points, GMA computes a geometry-based attention prior using relative coordinate offsets and distances, modulated by a global linguistic context. It then derives a binary attention mask via a trainable straight-through estimator, allowing each candidate token to selectively aggregate spatially consistent visual cues. We evaluated EG-3DVG on the scan-refer benchmark. As shown in tables 1 and 2, our model consistently outperforms existing methods, achieving state-of-the-art results in both bounding box localization and mask prediction. On the SR3D and NR3D datasets, Table 3 shows that EG-3DVG consistently achieves state-of-the-art results for both tasks. This slide shows qualitative comparisons between MCLN and our EG-3DVG. As shown in cases A and B, our framework effectively mitigates cross-modal misalignment. In cases C and D, EG-3DVG accurately localized the target despite distractors. Lastly, KC demonstrates that we successfully resolve geometric reasoning errors. Thank you for listening. Our official code and data are fully available via the GitHub link or the QR code on the slide.